This research project analyzes the accuracy of determining the bearing of a beacon relative to a camera. The two camera systems that will be compared are the forward-facing camera system and a catadioptric camera system. Both will be utilizing the PyCam V2 camera with a focal length of 3.04mm and a field of view of 62.2 degrees. An omnidirectional catadioptric camera system is comprised generally of an upwards-facing camera that focuses upon a mirror either conical, spherical, or parabolic with a custom profile. The mirror then reflects light from all directions around it and focuses it below on the camera lens. The testing done used a hemispherical mirror with a diameter of 50mm. The system will be modeled using Autodesk Inventor, as this software can be used to simulate a controlled environment and allows for precise camera options such as setting the focal length and field of view. The field will be a 2000 by 2000 mm area with a 400 mm high white wall surrounding it. The floor will be comprised of a green felt, and the beacon that will be detected is 50 mm in diameter and 150 mm tall. Further, it is colored bright pink such that it minimizes the detection difficulty on the software side. The beacon was placed in 7 different angles: 0, 5, 10, 15, 20, 25, and 30 degrees for both camera systems to observe. A constant distance of 750mm was used to separate the beacon from the camera. The 360-degree camera system was also subjected to 45, 60, and 90-degree tests to determine if there was a pattern to the error found. Note that the 360 camera angle test extension only goes from 0 to 90 degrees. This is because the spherical mirror will have the same error around the 4 quadrants in their relative places. Now that we have obtained the image from Autodesk Inventor, it is then imported into the MATLAB workspace. From here, it is fed to the region propping function, developed below, where it will return the beacon centroid position and the mirror centroid position. From here, it is able to calculate the angle of the beacon relative to the robot, the angle error relative to the known true angle of the beacon, and then the percentage error between the beacon's actual position and calculated position. Here is the region propping function, where it will mask the image for the beacon, and will also mask the image for the center point, or the mirror. It can also be noted that the error on the 360-degree camera vision system is periodic, with each maxima occurring at 45, 135, 225, and 350 degrees, and the minima of the error occurring at the multiples of 90 degrees, or the cardinal directions relative to the robot's camera. At all recorded points, the 360 camera has a significantly more accurate prediction to the bearing of the beacons. Furthermore, the average error for the 360-degree catadioptric camera was less than 4 times as much as the forward-facing setup when comparing over the dataset of 0 to 30 degrees in the 5-degree increments shown here, where you can see the resultant forward error in blue, the 360 cam error in red, and the full 360 camera error spectrum in green. In the data, there is a single error point of 6% at 30 degrees for the forward-facing camera. Because the lens has a field of view of 62.2 degrees from left to right, from center to right, it only has 31.2 degrees of view, half of the total. Since the center point of the beacon was located at 30 degrees, it is highly likely that the sides of the beacon would have extruded past the edge of reference and the frame of view that the camera saw, resulting in an accurate center point calculated by the software, and then a huge error as shown in the data results. In terms of determining the bearing of an object in the field of view, the 360-degree camera system, utilizing the hemispherical mirror, was drastically more accurate relative to the forward-facing camera system. However, what this report does not investigate is the significant loss of both viable range and range calculation accuracy that the 360 camera system suffers from. Due to the curvature of the spherical mirror, objects at an increased distance will shrink in the image faster than the same object viewed by a forward-facing camera system. This small change in pixel quantity as distance increases results in a significantly less accurate prediction from the distance determination. Further, the distance of the object generally must be derived from a predetermined function that was modeled using a known dataset, especially for custom mirror profiles, unlike the simple hemisphere used in this investigation. Further research topics related would include the comparison of the 360 camera system in its distance calculations versus the forward-facing camera system. Also, for extension research, the center of the mirror on the 360 catadioptric camera system reflects a view of the robot itself, which is camera sensor area that could be utilized better. By developing a custom profile, this reflection of the robot can be mitigated, and the view of the surroundings can be extended. The 360-degree camera system is significantly more accurate at determining the bearing of a beacon compared to a forward-facing camera system, as determined by the data and tests done in this report.